Great. Welcome back, everybody. I think I'll make a start now. So first up this morning, we're going to look at the syntax for parallel regions. So if you remember from yesterday, the parallel region is the fundamental parallel construct in OpenMP. And the code within a parallel region will be executed by all the threads. So the syntax looks like this for Fortran, ! $OMP parallel, followed by a block of code, and then OMP end parallel at the end of the block. So the restriction here is that the block of code has to be a structured block. So that means that you're not allowed to jump in or out of it. You can have the program could terminate inside there, so you could have a stop, but you can't have a means of jumping in or out without going through the end of the block or through the beginning, or get in through the beginning. For C and C++, it's #pragma OMP parallel, and then typically a block of code in curly braces. A couple of things to note about the C syntax. Unfortunately, because people are often used to this coding style, the opening curly brace cannot go on the end of the directive. The reason for that is that the code has to parse correctly as C code without the directive there. So the curly brace has to go on the next line and not on the end of the directive. Second thing to note is that what comes after the #pragma OMP parallel, strictly speaking, is a C or C+ structured block, and a single line of code without curly braces is a legal structured block. So that's allowable, but I would discourage you from writing code like that. It's then not completely obvious by glancing at the code where the parallel region ends. And it's also easy to fall into the trap of saying, oh, my original parallel region was just one line of code, but now I want to add a second line of code to my parallel region. So I just add a new line of code, and I forget to add the curly braces to enclose them and make sure that they're in the parallel region. And then you stare at the code for a long time, wondering why it's not doing what you want, because the second statement is actually outside the parallel region. So a single statement is allowed, but I would discourage you from using that facility. Okay, so just a reminder of how this kind of works. So we have remember that the master thread starts executing on its own sequentially. So for sketchy code like this, okay, so what will happen will be that the master thread will execute the function thread, then goes into a parallel region where the master thread creates or at least logically creates the additional threads. All the threads, and I've shown 4 here in total, all the threads, including the master thread, will execute the function Billy here. And then there's this synchronization point at the end. The master thread waits at the end of the parallel region for all the other threads to finish executing Billy, and then it carries on executing sequentially again with Daisy. Okay, so if we're just going to program with bare parallel regions and nothing else, which turns out to be a bit unusual, but it's still useful to know how to do that. And there are a couple of useful functions in order to be able to find out how many threads are being used and distinguish between the different threads executing. So this is a place where we're going to introduce the runtime library part of the API. So first of all, how many threads are being used? So this is returned by the function OMP get num threads. So in Fortran, in order to get access to the runtime library, so this is part of the standard. It's always the module is always called OMP_lib. So we need a use OMP_lib at the top of the routine. And in C and C++, again, the name of the header, the appropriate header file is always omp.h. So that's again standardized. So we have to hash include omp.h, and then we get to call. Then we can call omp get num threads. Important thing to notice is what the real meaning of this is not how many threads there might be or how many threads there will be in the future. The semantics of this function are how many threads are executing in the current parallel region. And so if we actually call this outside a parallel region in the sequential part of the program, it returns 1. So it really is how many threads are currently executing rather than how many threads. So it doesn't always reflect the value that you set in the environment variable. There is another function that will get you something closer to that, which I'll talk about later in the course. So this is really how many threads are there inside the current, how many threads are currently executing. And second useful function is to return the number of the executing thread. So again, and the choice of names here probably wasn't the best because they're a little bit similar. Okay, so the number of threads is OMP get num threads. The identifier of the thread is OMP get thread num. Okay, and for Fortran programmers, beware. Okay, thread numbering always starts from 0. Okay. And goes up to one less than what OMP get num threads returns. Okay. So as well as just the parallel directive, we can specify some additional information for the parallel region through clauses. So these are extra pieces of syntax that appear on the end of the directive. And there can be more than one of them, and you're allowed to separate them either with spaces or commas. So in particular, first set of clauses we're going to talk about is how to specify the behavior of variables. Are they going to be shared or private or something else? There are a couple of other options which we'll talk about later on in this lecture. But first of all, let's just think about distinguishing between shared and private variables. Okay, so inside a parallel region, variables can either be shared, okay, where all threads see the same copy, or private, where each thread has its own copy. Okay, so this is done with shared, private, and default clauses. So what you can do is you can specify shared and then a comma-separated list of variables in brackets, or private, again, comma-separated list in brackets. And you can also specify a default behavior. So anything, any variable that is referenced inside the parallel region and which does not appear in one of these clauses will take its behavior from the default clause. And you can either specify, in Fortran, you can specify default shared or default private or default none. In C and C++, for interesting technical reasons, which I won't go into, you can't do default private. So you either get to do default shared or default none. However, okay, let me make some comments about this. Okay, things to realize about this. On entry to the parallel region, private variables are uninitialized. So things that you put in a private clause, every thread gets a new copy of that storage, and that storage has uninitialized values. Okay, so something you need to be careful of. It's an easy source of bugs. Variables that are declared inside the scope of the parallel region are automatically private. Okay. And so for C and C++, that's often the more convenient mechanism of creating private variables, is simply to declare them inside the parallel region rather than declaring them outside and then having them appear in a private clause. So they're really equivalent, but from a coding point of view, it's usually better to have them declared inside. If they're variables that live, that really only live for the scope of the scope of the parallel region, it's better to declare them inside. All the accesses inside the parallel region are to those new copies. And so that means that you have this guarantee that after the parallel region ends, the original variable with that name is unaffected by any changes to the private copies. Okay. So the private copies create new storage for the duration of the parallel region. Each thread can modify its value. At the end of the parallel region, those private copies go out of scope. And then when we're back in the sequential part, we're left with the original storage with that name, and it still has the same value as when we went into the parallel region. So this works. This mechanism all works for objects in C++. So if you declare an object in a private clause, then you get a new copy for every thread, and that's going to be created using the default constructor for the class. Now, the next thing is probably what I think was the worst design decision in OpenMP, which was in there from the very beginning, and I think nobody really realized what a bad mistake it was. If you don't specify a default clause, it's the same as specifying default shared. So that means that any variables which you didn't declare in a shared or private or one of the other available clauses will be shared by default. And that's really dangerous. It's very easy to overlook some variables. They get shared by default when they should be private or something else, and you end up with race conditions. So I cannot strongly recommend enough that you always use default none. Okay, so and force yourself to declare everything that appears inside the parallel region. That might seem a little bit tedious, and it can be. You can end up with, particularly in sort of older style Fortran codes, you can end up with parallel regions which reference a lot of variables. But I think for the sake of avoiding potential race conditions, which are just horrible and potentially difficult to detect, then I strongly recommend that you always use default none and force yourself to think about every variable that's referenced inside the parallel region and specify whether it's shared or private or something else. Okay, so a rather contrived example, so something that we can do with just bare parallel regions and nothing else, and will fit on one slide. Okay, so what I want to do here is I've got an array. So here's a sketch of it on the right here. Okay, so it has, say, four columns, and I want each thread to write some values into a different column of this array. Okay, so here's my array declaration here. Okay, so it's 4 by 1,000, and so what I can do is, okay, I can have a parallel region. So I'm going to create a number of threads, and in this case I want to create 4 threads, and we can use the environment variable to do that, or there are other mechanisms to specify the number of threads, which we'll talk about later. But suppose I'm arranged it, so I'm going to create 4 threads here. So I get my thread ID, call OMP get thread num, and store that in a variable called myID, and then loop over the number of elements in the column and set the appropriate array values to 1. Okay, so let's think about all the variables which are referenced inside here. Okay, so we've got myID. Okay, so there aren't really hard and fast rules that you can decide whether things should be shared or private. It depends on the code and how they're being used. But clearly in this case, we want every thread to have its own storage to store its own thread number in. Okay? So myID needs to be private, so it can go in the private clause here. And we've got I here. Okay, again, every thread needs its own copy of I to iterate with, so declared I as private here. We have n. Okay, so n is just the length of the loop, or the number of elements in the column here. So that's not being modified inside the parallel region. So it's fine for that to be shared. It would be an error to make it private, because then we would get uninitialized private copies. And finally, we've got A. Okay, and it's okay for A to be shared because different threads are writing to different parts of the array, so there's no possibility of race conditions here. Okay, that's a rather old-fashioned and a slightly ugly way of writing C, so it would be more natural to do that and use the C language scoping here. So instead of having myID and I declared in a private clause, it would be more natural to declare them inside the parallel region like this. So int myID here and int I here. So those variables are then private by default because they're declared inside the parallel region. So this would be the more natural and nicer way to write this code in C. In Fortran, we don't have the luxury, so we need, again, same code. We need the private clause. Okay. Couple of things to note here. So of course you've got this, need to take care that we're using myID to index an array. Fortran arrays start at indexes start at 1, so we need to and thread IDs start at 0, so we have to take care of that. I've actually declared I as private here, which is correct, but it's actually not necessary. why is that? It's because loop iterators have a special status in the Fortran language, which they don't have in C or C++. They're C or C++, they're just any old regular variable. In Fortran, loop iterators are special, and OpenMP rules say that that loop iterators are private by default. So I don't need the I in the private clause here, but it doesn't hurt to have it in. Okay, any questions about that so far?
Hi, sorry, one thing I just wanted, can you hear me okay?
Yeah, sure.
Thank you, sorry. Well, one thing I just wanted to make clear and try to wrap my head around is with the function, when you check for the number of threads in the parallel region, the main thread, is that still taking up a thread? So if you ran something that had a program with 4 threads, and you check the number of threads in the parallel, would that return 3 or 4?
Return 4.
Return 4. So the main thread isn't taking up a thread in parallel regions running.
The master thread takes part in the parallel region. It becomes thread 0.
Right. Okay. Sorry. Yes.
Yeah. So it will create 3 additional threads. It becomes thread 0, and so the total number of threads executing inside the parallel region is 4, and that's what OMP get num threads will return.
Thank you.
Yeah. So Anti's asking, when I use an array in Fortran, for example, you assign it without index. Okay, so you basically use array syntax. I think the thing that's what you're asking is what happens if you do array syntax in Fortran. So can you do that? Yes, you can do that. There are mechanisms that allow you to exploit parallelism within array syntax, so to get to spread those assignments to different array elements over a number of threads. It doesn't get used very much, so and it's a little bit inflexible, and the implementations aren't necessarily that clever. So it's usual to actually, if you want to exploit parallelism over assignments to an arrays, it's usual to actually introduce an explicit loop for OpenMP. So you don't have to, but that's kind of the normal thing that gets done, is you have to introduce a loop. But if you just want, if you just want one thread to assign values to an entire array, then it's fine. Array syntax all works fine. Anything else? Okay, so just a little bit of syntax stuff is how to deal with how to extend directives over multiple lines. Because if I insist that you use default none and list all the variables in private and shared clauses, then we can end up with long directives. So it's often convenient to split them over multiple lines in source. So for Fortran, it depends whether you're in fixed source form, in which case the the continuation line starts with $OMP ampersand, or whether you're in free source form, in which case the ampersand goes on the end of the first line, and then we just have $OMP on the second one. In C and C++, it's the usual way. It just uses the usual rules for preprocessor pragmas. So we can continue it with a backslash at the end of the line, and then just continue with nothing, with no additional, without a second pragma, no new hash pragma. Just continue the directive on the line. The gotcha to be aware of here is that you cannot have any white space after the backslash. Okay, that will confuse it and cause an error. So it's one of those nasty things where that's just inherited from the C preprocessor syntax. How many columns should you consider? You're really an old school Fortran here. Okay, so yeah, you have to obey. If you're really an old-fashioned Fortran, then you and fixed format, you have to obey the column rules. Yeah. Okay. So far so good. What about, is there a way to initialize private variables? And the answer is yes, okay, because standard private variables are uninitialized at the start of the parallel region. If we want to have an initial value in them, and the natural thing to do is initialize them with the value that variable has at the moment where the parallel region begins, then we can use first private instead of private. Okay, so this is an alternative to private. We can specify variables as being first private, and then the private copies will be initialized with the value in the original variable as it was at the start of the parallel region. However, I should note that although you think, oh, that looks like a really useful feature, actually use cases for this are uncommon. Most variables which you want to be private inside a parallel region are going to be assigned before they're used anyway inside the parallel region. That's by far the most common pattern that you tend to see in code anyway. So use cases for first private, they do exist, but they're relatively uncommon. So if you think you need it, then I'd encourage you just to stop and think and say, is this really necessary? Is this really what I want? Again, this works for C++ objects, and in this case, the default copy constructor is going to be called to create and initialize the new object that every thread is going to get. Okay. So you need to, I guess, you can, things in this list, so private and first private, so all work with arrays. But you have to realize that there is some cost of making the copy. Okay, so essentially making private copies is almost free. Okay, not quite, but there is essentially zero cost to making a private copy for every thread. However, if we do first private, then there is some overhead to do with actually copying the values. So creating the storage is free, but copying the values is not. If they're scalar variables, the cost of the copy will be negligible. But if you have large private arrays, then making those copies can be a significant overhead. So you certainly don't want to do that if you don't need to. Okay. So again, this is a kind of strange and contrived example here, but suppose that we want to form the sum of every column in an array. Then we could do something like this. This is, as I say, it's a contrived example. It's difficult to find a sensible one that fits on a single slide. But suppose we have some value b with an initial value here. We could then declare that as first private, and then so every thread gets an initial copy of b with the value 23.0. It can then go ahead and use that and accumulate and add more values to it, and then at the end we can store that value in the last element of the column or whatever. Okay. And same for Fortran. Okay, so if we have an initial of b, that b has an initial value outside, we can declare it first private, and every thread gets a copy with the value 23, which you can then use inside the parallel region. Okay, so that's first private. Say use cases are relatively rare. So far we've got our possibilities for variables are shared, private, and first private, and there's one more, which is reduction. So if you remember from yesterday, reductions are these a pattern which produces a single value from associative operations like addition, multiplication, maximum and minimum, logical and, logical or. So what we'd like to happen is what we talked about yesterday. Okay, we'd like each thread to reduce into a private copy. Okay, and then at the end, the parallel region combine those private copies together with the appropriate operator to give the final result. So we can do this with the reduction clause. So this one's slightly different because we not only need a list of variables, but we also need to specify the operator that's going to be used. So the syntax looks like reduction and then operator colon a list of variables in brackets. This works for arrays as well as scalars, but the semantics of this is for arrays is that the reduction is done on each element separately, so that the result is still an array. Okay, it's not adding together the elements of the array to produce a scalar at the end. It's simply doing it's doing an individual reduction on every single element in the array. So that's no problem for Fortran. In C++, this is one of a few cases where there is this special OpenMP syntax to specify array sections. And the syntax looks like this. So if we have to specify the array and then in square brackets the first element, okay, so the number of the first element colon the number of elements. The reason for this is that in Fortran, the Fortran arrays carry metadata around with them, which describe their sizes and number of dimensions and so on. And in general, C and C++, arrays can just be effectively, if they're dynamically allocated, they're effectively just raw pointers. So the runtime has no idea how big they are, and therefore it has no idea how to create private copies or how big the private copies should be. So we have to be able to specify essentially the size of the have to be able to tell OpenMP runtime what the size of the array is, so it can create the private copies of the correct size, and that's done with this syntax. Okay. So in this example, okay, so what I want to do is form the sum of all the elements in my array. So I can do that with using the reduction clause. So I have some variable b, which has might have some initial value. It doesn't have to be 0. Okay, typically might be, but that doesn't have to be. So what happens here is that effectively, so the value in the original variable is saved. Okay, is unmodified at this point. By declaring b as a reduction with the addition operator, each thread will get a private copy of b, and those private copies will be initialized to 0. So the initialization depends on the operator. So formally, it's the initialization is to the identity element for the operator. So for addition, the copies will be initialized to 0. If it was multiplication, they'd be initialized to 1. If it's a max, then they'd be initialized to minus the largest, the most negative number, the largest negative number possible in the type. Okay, so minus huge, if you like. And so on. Okay, so the initialization depends on the operator that we specify. And all the accesses inside here are inside the parallel region referred to the private copies. Okay, and we can modify them in any way we like. There aren't any restrictions. Just because we said addition here, we can do anything we like to those private copies. We can add stuff, subtract stuff, modify it in any way we see fit. But at the end, what happens is all the private copies are then added back into the original variable. Okay, so after the parallel region ends, B will contain the value 10 plus the values of plus some of the values of all the private copies on every thread. So that looks slightly weird when we're just dealing with raw parallel regions, but we'll see you'll see when you come to use it with parallel loops, then that turns out to be the kind of the natural behavior. Okay, same example in Fortran. Okay, so Anthony asks, can the reduction be requested for more than one variable? Yes, you can have a list of variables in there. If you want variables with different operators, then you need more than one reduction clause. Okay. So you can have reduction plus colon B, and then reduction max colon Z for another variable. Okay. If it's the same operator, you can just have a comma separated list in one clause. If you need different operators, then you need multiple reduction clauses. Okay, anything else to say about reductions? Yes, okay. So there are a restricted list of operators that you can use. Say addition, max and min are by far the most common. Max and min in more recent versions of OpenMP, max and min are defined in this context for C and C++. Because they're not built-ins they're not intrinsics in the language, but you can still specify them in reduction operators, and they have their normal meaning in terms of they're effectively defined to be the usual macro that you implement for max and mins. You can only do reductions on basic types like this. Okay, if you want to do reductions on structures or objects, then OpenMP does have a mechanism for doing that, but it requires you to write some OpenMP syntax to define the reduction operator. Okay, there is a way of doing that, but it won't just work out of the box. Okay, you can't just overload the plus operator for a class and expect the reductions to work. You need some additional syntax for that. And Daniel asks, in this example, shouldn't the variables c and n defined as shared? Aha, they are shared by default because there's no default none clause. I've been lazy. So is the directive case sensitive? No. In Fortran, no. In C, yes. Fortran, no. You can have lowercase directives in Fortran. That's fine. Yeah. So I'm being lazy here and using the default scoping for C and N here, which is shared. Just to save me space on my slide, really. I'm setting a poor example. Okay, so that's enough for you to get started on the practical exercises for real. Okay, so the first example is just to do a fairly simple piece of code, just using what I've taught you in this lecture. So just using parallel regions, shared private and reduction clauses, and the functions to return the number of threads and the thread ID. Okay, so that's enough to be able to solve this problem. And the example is just to introduce it very briefly. Is the code I'm giving you is a little short piece of code. What it does is it estimates the area of the Mandelbrot set. Okay, so I'm sure you'll all be familiar with the world's most famous fractal. Okay, I guess from a mathematics point of view, what's not actually totally obvious is that it does have despite having a fractal boundary, it does have a mathematically well-defined area. There is no known analytic expression for the area, so all you can do is estimate it numerically. You can do it in more sophisticated ways than this, but this is a very simple, like 10-line code. So what we basically do is draw a box around the outside of the Mandelbrot set. Well, actually, we just do half of it because of the symmetry. And then we basically generate a grid of complex numbers inside the top half of the box. Okay, and then basically just test each of those points on the grid to see whether it's inside the set or not. And then just the ratio of the number of points inside the total number of points multiplied by the size of the blocks gives us an estimate of the area. But this is a nice, almost trivially parallel problem because the testing of the points is independent. Okay, so we can get different threads to test different points in parallel and get some performance improvement from it. Okay, so yeah, when the time comes, so I should have some time at towards the end of today's session for you to work on the practical exercise if you want to. As I say, it's the way this course is set up, then if you prefer to do that in at your leisure in your own time, then that's totally cool. Absolutely fine, no problem. Okay, does anybody have any more questions so far? Okay, in that case, I suggest we take a break and okay, let's resume at 11 o'clock. We're not under too much time pressure this morning. Great, welcome back everybody. So now we're going to look at work sharing directives. So what we've seen so far with using parallel regions is that it's possible to do stuff sensibly, but it's all a little bit awkward. We have to, if we just use a parallel region, then essentially in order to do useful things in parallel, we need to get the number of threads, get the thread ID, and then to manually figure out which thread's going to execute what based on its ID. That's all fine. It's a slightly inconvenient way of programming. I do recommend that you do that first of all in the practical example, just to make sure that it's you get it absolutely clear in your mind how parallel regions work in OpenMP. But that's not typically how they're used most of the time. And the reason for that is that OpenMP supports work sharing directives, which essentially do that division of work between threads more transparently and more readily for you. So work sharing directives are directives which appear inside a parallel region, and they indicate how work should be shared out between threads rather than just every thread executing the same block of code. So by far the most important one of these is the parallel do and for loops, which we'll talk about first. Then I'll also talk about single and master directives at the end of this session. So parallel do loops. Okay, so as we mentioned yesterday, loops are the most common source of parallelism in most codes, and therefore parallel loop directives are really important. If you look at OpenMP codes out in the wild, particularly in HPC and scientific application space, then most of the OpenMP directives you see are parallelizing loops. Probably, upwards of 95%, if I had to guess, of OpenMP directives are parallel loop directives. So what does this do? It basically does something very straightforward. If we have a loop inside a parallel region, then we have the ability to divide the iterations of the loop between the threads instead of every thread executing the whole loop. So the loop directive appears inside a parallel region. It indicates the work should be shared out between threads instead of being replicated. There is a synchronization point at the end of the loop. Okay, so all threads have to finish their subset of iterations before any thread can proceed with the next piece of code, if there is one, inside the parallel region. So this is a point where there is a barrier synchronization. There is an implicit barrier at the end of the work shared loop. That's there by default. You can get rid of it if you want to. We will talk about that later. Okay, so what does the syntax look like? So for Fortran, it's $OMP do with some optional clauses, some of which we'll talk about in a bit, followed by the do loop. And then optionally, $OMP end do. Okay, so the end do is not required because the compiler can perfectly well figure out where the loop ends. It's therefore convenience stroke nice formatting. So it's just most other OpenMP constructs in Fortran have a start directive and a directive and then an end directive at the end. So it's really just to make if you want to put the end do there to make your code look tidy and neat, then fine, feel free to use it, but it's not necessary. So in C and C++, it's hash pragma OMP4 immediately followed by the for loop. So one gotcha here to remember is that the for loop cannot have enclosing curly braces. Okay, so it's not like a parallel region where you have hash pragma OMP parallel and then open curly brace. Okay, it's hash pragma OMP4 and then the next line must be the for statement. Okay. Fortran, it's pretty straightforward, but in C and C++, there are some restrictions on what we can do with this syntax. And that's because the for loop in C is really just a general while loop, okay, with some convenient syntax imposed on top of it. So there are restrictions on what we can do, okay? And these restrictions are there to basically ensure, like we talked about yesterday, that the number of iterations, so the trip count, can be calculated before the loop starts executing, which is not true in general for general for loops in C. So basically, it has to have this sort of canonical form. So it has to be for some variable equals some initial value. The test has to be the variable is less than or equal to, greater than equal to some other value. Not equal is allowed these days, actually. That's a sort of C++ idiom, is to do not equal, but that is permitted. And then some increment expression that looks like, variable equals variable plus or minus something, or the usual semantic equivalents like var plus plus or plus plus var or var minus minus. And the other restriction is that the loop iterator variable cannot be modified inside the loop body. Again, that's legal C or C++, but is not allowed if we want to have a OpenMP4 directive on it. Okay, so this means that we have a very nice, straightforward way of parallelizing loops. So think about a loop like this, where we have essentially independent iterations. Okay, so the calculation of every element of BI here is independent of every other one. So it's a nice independent parallel loop. So what we always need to be inside a parallel region in order to create the threads. And then we can put in Fortran a do directive, or in C, C++, a for directive in front of the loop. And that will mean that the loop iterations get shared out between the threads rather than every thread executing all the iterations of the loop. So it turns out that this pattern, or this pattern of constructs is so common. Okay, so you want a loop, so you want a parallel region and a work sharing directive. It's such a common pattern that there is a shorthand form which combines them both. So you can, in Fortran, you can say OMP parallel do, or in C and C++, #pragma OMP parallel for. And that combines both the parallel region and the work sharing directive into a single directive. So for that same example, you can tidy it up a bit and make it look neater and code it like this. So that's nice, but that's also potentially a little bit confusing as well. Okay. So some more things about it. Okay. So you can have the work sharing directive. You can have private, first private, and reduction clauses on it, which refer just to the scope of the loop. Private and first private are fairly unusual. What is a relatively common use case is the ability to do the reduction just for the scope of the loop. Because what can often happen is that you require the result of the reduction later on in the parallel region. If there's more than just the single loop inside the parallel region, it's quite common, quite common situation where you want the result of the reduction to be calculated and used somewhere later in the parallel region. So it's not sufficient, it's no good having the reduction clause on the parallel region, because then the final reduction operation doesn't happen until the end of the parallel region. You really want it to happen at the end of the loop. Okay. The parallel loop index is always private by default. So as I mentioned earlier today, all loop indices are private by default in Fortran, but not in C, C++. So most of the time, the usual idiom is to declare the variable, declare the loop iterator inside the for statement. So you do for int I equals whatever. In which case, if that's inside the parallel region, then you get private variable by default because of the scoping rules. So otherwise, the combined directive is able to take all the clauses available for the parallel directive. Okay. But as I say, this combined directive is useful, but just beware that there are three different things. Okay, so parallel do or for is not the same as do or for, and is always not the same as parallel. It's a combination of both of them. Okay, any questions so far? So Jason is asking, is the loop index still private after adding default none? Yes, it is. Yeah, default none doesn't affect the default behavior for loop indices. Yeah. Obviously, so behavior is somewhat compiler dependent, but compilers are actually pretty good at error handling with default none. So if you miss something out, if you specify default none, and you miss something out that you should have declared, then compilers are generally very good at generating error messages for that. Okay, the compilation will fail, and you'll get a message saying, you know, default number specified, but variable X does not appear in any data attribute sharing clause, or some, you know, some such message like that. So compilers are pretty good at catching those errors, and they're fairly easy to understand what the compiler's telling you. Anthony asks, can we manage the bunch of indexes inside the loop? I'm not sure what you mean by that. Do you mean if we have nested loops and more than one loop? Ah, okay. So say, do you mean how can do we have any control over which threads execute which iterations? That's what I'm about to talk about next. That's just coming up. Okay, good. Okay, so yeah, let's carry on with that then. Okay, so if we don't specify any additional clauses, then the work sharing loop directive will partition the iterations as equally as possible between the threads. Okay, so you know, typically it won't divide exactly by the number. It may not divide exactly by the number of threads. So there's some question of how you deal with the remainder, and that's not specified by OpenMP. Okay, so as if we have, say, a loop with 7 iterations and 3 threads, then it could get partitioned as 3 and 3 and 1, or 3 and 2 and 2, and we actually don't know which what's going to happen. Most implementations will tend to do the 3 and 3 and 1 thing, because solely for the reason that the integer arithmetic is slightly simpler, okay, and slightly cheaper to do the first thing, rather than try and spread the remainder out. But say mostly we don't care, and you don't actually know for sure what's going to happen. So that makes total sense, provided the loop iterations are well load balanced. If every loop iteration is going to take more or less exactly the same time to execute, then the default behavior is what we want. We want to share the loop iterations as equally as possible between the threads. But of course, that's not always the case. In many loops, there will be some load imbalance. So some loop iterations may take longer than others to execute. So in that case, we need to think about applying a schedule clause to the loop. And this gives us a variety of options for specifying an algorithm by which the loop iterations, specifying which loop iterations are executed by which thread. So the syntax, so this is a clause on the do or for directive. So OMP do schedule, and then in brackets a kind, and then optionally a comma and a chunk size. Okay. So kind can be, there are 5 possible values for the kind, okay, and I'll explain what those mean in the slides coming up. and some of those options also take a chunk size parameter, and so the chunk size is a positive integer. So this is a valid example. So OMP do schedule dynamic, 4 is a valid example. Okay. So the first option for the schedule kind is static. And if we don't specify a chunk size, then effectively we get the same as the default behavior. The iteration space is divided into approximately equal chunks. Okay. Chunk is just a contiguous subset of loop iterations, and one chunk is assigned to each thread, and it's done in order. Okay, so the iterations have a natural order in which they would be executed sequentially. So the first chunk of iterations is always guaranteed to go to thread 0, and then the next chunk to thread 1, and so on. If we do specify a chunk size, then what happens is the iteration space is divided into chunks, each of that size, and those chunks are assigned cyclically to each thread in order. Okay, so thread 0 gets the first chunk, thread 1 gets the next one. Okay, and then when we run out of threads, they cycle back to thread 0 again, and so on. So this is a block cyclic schedule. Okay, easy to explain with a bit of a diagram, I think. Okay, so suppose we have a loop with 46 iterations in it, and we are executing with 4 threads. So if we specify schedule static, then what we'll get is as near as equal division as possible. Okay, so most likely what will happen is that thread 0 gets 12 iterations, so does thread 1, so does thread 2, and then thread 3 will get the remaining 10. If we put a chunk size in there, so if we specify schedule static, 4, then we get chunks of 4 iterations. So the first 4 go to thread 0, the next 4 to thread 1, the next 4 to thread 2, the next 4 to thread 3, and then we cycle back to thread 0 again. So 0, 1, 2, 3, and so on until we get to the end. And if things don't divide nicely in this case, so we'll be left with a chunk of 2 iterations. The final 2 iterations will be executed by thread 3 in this case. Okay, so our next option is dynamic. Okay. So this also divides the iteration space up into chunks of the specified size. But instead of doing a cyclic distribution, it assigns them to threads on a first come, first served basis. Okay? So what that means is as a thread finishes a chunk, it's then assigned the next chunk in the list. And if the chunk size, if we don't specify the chunk size, and then for dynamic, then it defaults to 1. So we get individual iterations being assigned to threads on a first come, first served basis. And we'll come to example in a minute, because also want to introduce the guided option for the schedule kind first. Okay, so this is similar to dynamic in the sense that it's also a first come, first served algorithm, but instead of having all the chunks the same size, and for guided, the chunks start off large and then get exponentially smaller towards the end of the loop. So a more precise specification is that the size of the next chunk is proportional to the number of remaining iterations divided by the number of threads. Okay. And the constant of proportionality is up to the implementation, but almost all implementations use a half. Yeah. So the size of the next chunk is the number of remaining iterations divided by the number of threads, and then divide by 2 again. In this case, the chunk size just specifies the minimum size, and again, it defaults to 1. Okay, so let's look at our example loop again with 46 iterations and 4 threads. If we specify a schedule with dynamic and a chunk size of 3, then we will get we'll get chunks of 3 iterations. So the first 4 chunks will get assigned to different threads. But then suppose thread 1, which is the black one here, finishes first, it will get the next one. And then suppose the gray one, so that's thread 3, finishes next, it will get the next one in order. Okay, so whichever thread finishes its chunk, it picks up the next one in sequence. So if we specify guided with a chunk size of 3, then the chunks start off large. So initially there are all the iterations are remaining. So the number of remaining iterations is 46, and so we will get so we'll divide that by 4, and then divide by 2 again to get the initial chunk size. Okay, so the chunk sizes get progressively smaller and smaller as we go along, but they won't get smaller than 3 because that's what we specified here, except possibly for the last one, of course, if things don't divide nicely. So options, so we've seen so far, we've got static, dynamic, and guided. The fourth one is auto. So auto basically says, okay, this just lets the runtime do whatever it feels like. It lets the runtime have freedom to choose its own assignment of iterations to threads. It doesn't have to be one of the other schedules. It can do anything it wants. So the intention of this is a couple of things. So one of them is what I've said here is that if the parallel loop's executed many times, then it's possible for the OpenMP runtime to do some dynamic learning about the loop and evolve a good schedule. It's also, and perhaps more commonly used, as a mechanism by which the implementations are allowed to implement something different. Okay. But without extending the specification. So it allows implementations the opportunity to use a different algorithm which isn't static, dynamic, or guided, and yeah, that'll be in the compiler document. What it does will be in the compiler documentation somewhere. And then finally, runtime. So it's not really a different option. What it does is it allows the schedule to be set using an environment variable rather than encoded in the code itself. So the relevant environment variable here is OMP underscore schedule. So we can set that before we execute the program, and so maybe set it to dynamic 1. So that means any loops that have schedule runtime in the code will use the dynamic schedule with a chunk size of 1. So the rationale here is that it makes it convenient for you to experiment with different schedules and chunk sizes without having to rebuild the code. But it's really something that you should use in development, in code development, and not leave in there for production code. Okay, so you probably don't want to rely on whoever's using the code to set the environment variable appropriately. In most cases, it's something you want to use to experiment in production. Sorry, in development to figure out what a good schedule is, and then put that in the code for production. Okay, so that's a lot of options. How do we make sensible choices? Well, in practice, we often end up just doing some experiments, but here at least are some guidelines of when we're likely to want to use each of these schedules. Okay. If your loop is well load balanced, then there's almost no reason to do, let's say almost, okay, some qualification there. Almost always you want to use static, or just leave the schedule clause off, okay, because that has the least amount of overhead. Let's say there are cases where that's not quite true. We'll talk about one of those cases in the performance session next week. So static with a chunk size it tends to be good for loops that have some sort of mild or smooth in load imbalance. So in other words, where there is some correlation between the loop index and the amount of work in the loop iteration. And that's a reasonably common pattern. Okay, so it's quite common to have, say, triangular loop nest where the number of inner iterations, the number of iterations of the inner loop is proportional to the outer loop index. Okay, so the amount of work is essentially a linear function of the loop index. And so in cases like that, then static with a chunk size can be a good option. Okay, but it can introduce some overheads. So in particular, if you choose a small chunk size, then it can interfere with sequential optimizations like vectorization. So you have to be a little bit aware of that. And there are other overheads that it can cause as well. Again, we'll return to these to some of these ideas in the performance session. Dynamic is typically useful if you have loop iterations with very widely varying loads. So if some loop iterations take 100 or 1,000 times longer than others, so you have, and it's not, there isn't a clear correlation between the loop index and the amount of work, then dynamic can be useful. Downside is it has higher overheads because threads have to synchronize to determine safely which thread gets the next chunk, and it also ruins data locality as well. Again, something we'll talk about in the performance session. So guided is kind of compromise. It's less expensive than dynamic in terms of its implementation, and it will balance the load in a lot of cases, but there are cases where it doesn't work. Okay, so because it starts off with large chunks which get smaller and smaller. If you have a loop where the early iterations are the most expensive, using guided might not balance the load very well for you. And as I mentioned already, so auto allows compiler specific options. So it allows the compiler or the OpenMP runtime to implement something different than static, dynamic, or guided if it as it sees fit. Okay, any questions about loop schedules? So the practical exercises give you, well, at least a couple of opportunities to experiment with them and see what happens. And we will return to some of the issues about choosing between different schedule kinds and the sort of things that can go wrong performance-wise in the performance session next week. Okay, let's move on and look at another couple of constructs. So talk about single and master here. Okay. Oops, gone too far. So the single directive. So this is a way of indicating that although that we're inside a parallel region, there's a block of code that we want to be executed by only one of the threads and not all of them. So the way single works is that the first thread to reach the single directive will execute the block of code. And there is, again, so like the loop construct, there's a synchronization point at the end of the block. All the other threads will wait until the block has been executed. No big surprises with the syntax here. Okay, it's just for Fortran, single and end signal enclosing a block of code, and C and C++, hash pragma OMP single followed by a structured block. Okay, so here's some code, or some rather sketchy code here, which gives you some illustration of why you might want to use, in a case where you might want to use single. Okay, suppose we have a parallel region, and then we get every thread executes this setup function on some data structure X. Okay, so can you imagine here that X is maybe a pointer to some data structure, and all the threads are going to call setup on X and do something different depending on the thread number, or there's a loop inside there which is going to get shared out, or something like that. And then after that, we want to read some values into a different data structure Y and want to read them from file. Okay. And so we only want one thread to do the read from file, and so we can enclose that in a single. And then after that's happened, then we want threads to do some more call another function that uses both X and Y. So what will happen here is, suppose we have 4 threads. So all 4 threads will call setup. Whichever thread finishes setup first, okay, so we might not know which one that's going to be, it will go ahead and call the input function. So it will enter the single construct, call the input function. All the other threads will skip over input and wait at this implicit barrier at the end of the single block. So they'll wait at the end of the single block here. So they might be idle for some time until input has happened. And then once input completes on thread 1, then the barrier then completes and releases all the threads that can go ahead and call work. There are some other use cases as well. So we'll see some of them. We'll see some of them later on in at least one of the practical exercises has a case where where it's convenient to use single, where we need one thread needs to initialize inside a parallel region. We want one thread to initialize a value, and then the other threads have to wait until that initializers happen before they use that shared variable. Okay. Yes, you can have, so not unusual to require it. You can have private and first private variables on singles, and again, it's like most things, it has to be a structured block. You can't branch in or out of it. Okay. So we've spoken about these implicit barriers at the end of work sharing constructs, so do or for or single. So if you wish to remove that implicit barrier, then you can do that with a no wait clause. However, you need to be very careful. You're removing a synchronization point and therefore potentially causing race conditions if that barrier was actually necessary for correctness. So yeah, it's possible, and that should be something that you do as part of. It really should be something you do as part of performance tuning, rather than sort of second guessing. Oh, that barrier is going to be expensive, therefore I need to get rid of it. Yeah, it's really a sort of a performance optimization rather than something that you should try and use as much as possible. So it works in Fortran. The no wait clause goes on the end do. So this is a case where you actually do it forces you to actually code the end do, which is, well, that was the choice that was made. Can like it or not like it. C or C++, it just goes on the for directive, so for no wait. So what this means is that instead of waiting for all the other threads to complete their loop iterations, as soon as a thread has completed all its subset of loop iterations, it will then just carry on executing inside the parallel region. Okay. And there is an example in one of the exercises as well where this turns out to be a neat solution in certain cases. Okay, so the last thing I'm going to talk about is master. Okay, so this is kind of similar to single, but different in a couple of important ways. So first of all, it also indicates that a block of code should be executed by one thread only. But in this case, it's not the first thread that gets there, it's explicitly thread 0. Okay, so it said this block of code should be executed by the master thread. But for, again, reasons that go back to the very beginning of OpenMP and aren't really, it's not really clear why this choice is made, there isn't synchronization at the end of the block. So for the master, the other threads skip the block and continue executing. So it's different from single. So this is, there is a way to add a barrier at the end. We'll talk about that in the synchronization session as how you can do that. But there's this kind of funny asymmetry. Okay, so single has a barrier by default, which you can get rid of with a no wait clause. Master has no barrier by default, but you can add an explicit one if you want to. Yeah, again, it's one of those design decisions that was made at the very beginning of OpenMP. It's difficult to change without breaking codes. So we're kind of stuck with it. And in hindsight, it probably doesn't make a whole lot of logical sense. No surprises with the syntax. Okay. Any questions about single or master? Okay, so the next exercise is basically just to redo the Mandelbrot example, but use a work sharing do or for directive instead of just using the bare parallel region and explicitly calculating which loop iterations are going to be done by which thread. Okay, but I would encourage you to do it that way around. So do the difficult one first, and then experience the joy of being able to use the work sharing, and you should find that you can do it by just adding a single, not a single directive, but one exactly one directive, one line of OpenMP to the original sequential code, which will take care of everything you need for you. Okay, so if there aren't any more questions, then again, so as with yesterday, I will stay around on the session until 12:30. So if anybody wants to hang around and start the practical exercises and get any support with that, then please feel free. But otherwise, also if you have other things you prefer to do with your time, then I'll hopefully speak to you again on Thursday. Okay. So outside of this session, if you got any questions about the practical exercises or anything else, please post on the chat that's linked from the course webpage. I'll also post the link directly just now.